So here I'm going to give an example of how we can be confident that our sample comes from a known population. What I'm going to do here is create a different population I'm going to call X, and it's going to use R's random normal generator. So what this is doing is R norm is it's saying generate a random normal distribution of 100 observations with a mean 50 and a standard deviation of 0.5. If we look at what X is, it's a whole bunch of random numbers. And if you took the mean of all these numbers, right, mean of X, you're going to get 50, and the standard deviation is going to be 0.5. And what we can do is we can plot this in a density function, and let's look at the graph here, and it looks like this, right? So this is the density, 0 to 1, and these are the different values that you see in the matrix here that go from some about 48 all the way up about 52. And you can see most of the observations are around 50 where that mean is. We could plot this a little differently if you're saying, well, this looks like there's a lot of variation here. If we plot it with and change the x-axis scale to what's 45 to 65, we can see that this distribution becomes much more narrow. The mean is still around 50. The variation is still exactly the same, standard deviation of 0.5, but just by changing the scale, you get a little different picture here of what the data looks like. So what we want to do is take a sample of 5 observations from this population, right? And these are the observations we get: 50.9, 49.7, 49.85, and so on. We can take the mean of that, and we get 49.89. We can do that again a second time. Here we get a mean of 49.9. Now, how can we tell or indicate some confidence that the sample we took came from this population? What if we didn't know the population in which we took the sample from? Could we say that this sample here, with a mean of 49.89, came from this population that we generated here? So what I want to do is take essentially 100 samples from this population. And what I need to do first is create an object called saved means, and it's going to be a matrix with 1 column and 100 rows. And so I'm going to tell R to do that now. And if you look at what this object is, it's just an empty vector, really. Right? So 1 column, all it says is NA, that means there's nothing in the columns, and 100 rows. And I'm going to store means there. And so what I'm going to do here is use R's loop function, and just for I in 1 through 100, so just loop through 100 times. And what it's going to loop through is it's going to take a sample with a size of 5, just like we did before up here, from the population X that we just generated. And it's going to save that into an object called S. And then I want to take the mean of S and save it in this empty matrix. So what it's going to do is simply take a random sample of 5 observations from X, and then store it in this empty sort of matrix or vector here. And it's going to do that 100 times. Okay, so it just did it. And then let's look at what actually happened. If we type in save means, we now have means in our rows and columns here from 100 different samples. And we can plot that in a histogram. We can plot these means in a histogram. And what it looks like, what we can see here is that most of the sample means that we drew, most of the samples that we drew had a mean of 50 or to 50.2, right? We had very few samples that had a mean of 49.2, and a few samples, right? We can see it's about 10, 11 samples that had a mean about 50.6. What we want to know is how confident we could be that any one of these samples came from this population. And what you could do is you could calculate the confidence intervals. And what you do to there, and you'll probably do this calculation quite a bit, is take the mean, 50, plus the standard deviation, which is 0.5, times 1.96. Now, why 1.96? Well, we know that 95% of the distribution lies within 1.96 standard deviations of the mean. And so we get this from the standard normal distribution table from the previous chapters on probability. And this gives us the upper bound limit. And so what this says is that when we do the calculation, it says that 95 out of 100 samples that we draw from this population should have a mean at 50.98 or below. Right? 95 out of 100 times, if we take 100 different samples from this population, we should observe that 95 of those samples have a mean below 50.98. And then we just do the same thing here, but except we subtract, right? We take 50 minus 0.5 times 1.96. Run that calculation, we get 49.02. And what this says is that 95 out of 100 sample means that we draw from this population should have a sample mean above 49.02. Right? And so what we get is what we call 95% confidence intervals, right? 95 out of 100 samples should have a sample mean that lies between 49.02 and 50.98. Now, we picked 95 out of 100 because as researchers, we get to choose how confident we want to be in our estimates and in our inferences. If I was doing medical research, I might want to be confident 99 out of 100 times. So then I would look up in the normal table and change this value. This 1.96 would probably be something like, I think it's like 2.06 or something like that. It would change. But for most social science research, we want to use the 1.96 value simply because we want to say we're confident 95 out of 100 times. It could be 90 out of 100 times, and we could change this. Okay, so then what we'll do is we'll sort the saved means, and do we have any observations below 49.02? We don't. And what about 50.98? We don't. So here we drew 100 sample means, and 100 out of 100 of those sample means lie within the 95% confidence intervals. So if we were to draw any one of these sample means, we could say that we are 95% confident that it came from this population.